morning. I want to continue our discussion on solutions, and if you continue in the sciences or you have a career in the healthcare industry or in the science field, then what's going to be very important is that you understand what is soluble in water and what is not. And I like to use, or many people like to use, the phrase like dissolves like, which means that water, which is polar, will dissolve other polar molecules. But it's not always true, and I think I'll have time to show you some exceptions, some notable exceptions. Okay, I mentioned that water is polar, and it can dissolve other polar molecules. So this term, or this phrase, like dissolves like, basically means that since water is polar, it should dissolve other polar molecules. Let's take a look at why water is polar. You have water, and this should be reviewed that the Lewis structure looks like that. And it's bent. It's bent. Oh, maybe I need to give us a key also. Anytime we see a green arrow with this hash, we're going to call that a bond dipole. And it's mainly going to be determined by electronegativities. If there's a big difference, then you have a polar bond. If it's identical, the electronegativities of the two atoms, or if they're very similar, then it'll be nonpolar. But when you add up all the bond dipoles, you get what's called a molecular dipole. And we'll designate that, maybe green and red is not the best case we should use. um, right, because I think some people are red-green colorblind. I'm hoping you can see the difference between green and blue. Molecular dipole. It's the addition of all the bond dipoles. And you're looking for a net molecular dipole. Let me illustrate with water. Oxygen is definitely a lot more electronegative than hydrogen, and you'll have these bond dipoles. The molecular dipole is the net movement up. Okay, so the left and right directions cancel out, but there's a net up direction. There's no net down. There's no down direction of the dipole to cancel that out. So overall, you could write this molecular dipole anywhere you want. Just know that it has a non-zero molecular dipole, and therefore this is polar. When you have a net molecular dipole, okay, you are polar. Now there's going to be gradations. Some molecules are very polar, some molecules are slightly polar, and we're going to practice that. This is one of the skills where it is essential to practice, because there are exceptions that we'll see in just a bit. So it has a net molecular or net molecule dipole. Our conclusion is this is a good polar solvent. Okay. The plan is to give you a couple of polar solvents, a couple of nonpolar solvents, and then start throwing stuff into it and see whether it dissolves or not. So another polar solvent could be something like ammonia. That's also polar. Because if we draw the Lewis structure, again, why are we drawing the Lewis structure? Because shape is important. And I'm using these wedges and dashes to indicate hydrogen's coming towards us and away from us, but it's not planar, it's trigonal pyramidal. So you do have this net, upward movement. And your net dipole, or your net molecular dipole is going up again. Methanol. So methanol is interesting because it does have areas that are nonpolar, but also areas that are polar. So obviously it's the oxygen that's more electronegative, and you'll draw bond dipoles on both sides. So there is a net molecular dipole, and it's kind of going, because I have this tilted, it's kind of going slanted up in the direction of the oxygen relative to the two atoms next to it. Okay, methanol. Ammonia is typically a gas, but you could also make it a liquid with a little bit of pressure. So liquid ammonia is a good solvent. Let me go over nonpolar solvents. Let's use purple. Don't worry, I know that some of you are expecting a discussion on intermolecular forces. How do these solvents surround or solvate the solute? And we mentioned before that's via intermolecular forces, attractions. Nonpolar solvents. A very popular one is benzene. I'll use purple still. Benzene has a formula of C6H6, and most textbooks don't expect you to know what it looks like, but I think that's silly. Let me show you where the 6 carbons and 6 hydrogens are. It's a flat molecule, and you have these double bonds. What makes it nonpolar? What makes it different than the others? We don't have a net molecular dipole because we should remember that a CH bond is considered a nonpolar bond. It has a nonpolar dipole, or we'll call it nonpolar bond. And you might know it as a nonpolar covalent bond. That's because the difference in electronegativities for C and H is very small. It's around 0.4. So the cutoff is typically 0.4. If you have an electronegativity difference between 0 to 0.4, that is a nonpolar covalent bond. Where are these numbers coming from? Okay, so again, this is the difference, the delta electronegativity. We're getting electronegativities from the Pauling electronegativity table. I don't expect my students to memorize it. I do expect my students to know that carbon and hydrogen bonds are nonpolar, whereas carbon nitrogen, carbon oxygen, hydrogen nitrogen, hydrogen oxygen, since nitrogen and oxygen are fairly electronegative, that those are polar covalent bonds. What do we have so far? We have 3 polar solvents. We have 1 nonpolar solvent. Let me give you another one, and you'll definitely start to see a trend. Hexane. Hexane has 6 carbons, and we'll zigzag it. And the rest of the 4 bonds of each carbon are going to be hydrogens. Another molecule with only carbons and hydrogens. So I will say that hydrocarbons, molecules that are made only of hydrogen and carbon, are nonpolar. We're about to look at some textbook problems, but let me see if I could feed you some notable examples. How about ethanol? So ethanol, I'm going to draw the condensed structure. ethanol, and it has a CH3 group, a CH2 group, and it has an OH. Is it soluble in water or benzene, or both? So the question is, um, water soluble or benzene soluble? You're going to say that ethanol has hydrogen bonding. So we'll do this in order. All molecules have London dispersion attractions. This molecule is dipole-dipole because of the carbon-oxygen dipole. And I'm just talking about with itself. Okay, we're going to determine water or benzene in just a bit. And it has OH, hydrogen bonding. The purpose of this is to conclude that this ethanol is polar. And therefore, symbol for therefore, the three dots, therefore more water soluble. Okay. But let's go higher. Let's go to pentanol. I'm running out of space. But CH3, CH2, CH2, pent is 5. So we have 5 carbons, and then OH. And technically, it's 1 pentanol. That's an N. Well, the issue is we still have this hydrogen bonding part. And you could hydrogen bond to what? To water. It would determine whether it's more water or benzene soluble. But the issue is all of this looks like a hydrocarbon. So all of this is nonpolar. And it's a large part of it. I'll give a general rule in just a bit about can we determine if we have how much larger does the hydrocarbon part have to be for the molecule to be nonpolar. I'll give you that in just a bit. But the conclusion is this is nonpolar, this molecule, and it's more benzene soluble. Not water soluble. Let me state a rule then. Again, this one I'm making up just from experience because I want to know is there a general rule to determine, well, why is that water soluble and why is this benzene soluble? How many carbons do I need to make it nonpolar? Is probably a better way to say it. Okay. I'm gonna say if you have a ratio of oxygen slash nitrogen slash fluorine, chlorine with halogens to carbon of, let's say, 1 to 4 or better. Whoops, yikes. 1 to 4 or better. So if you have 1 oxygen for every 4 carbons, then you're going to be polar. So 1 to 4 or more. Like maybe it's 2 to 7. It is the ratio. 25%, maybe, if I could say it. If you have 25% of ONFClBr compared to carbon, then you are polar and water soluble. You can tell I'm making up this rule because I'm just thinking off the top of my head, of 25% or more, you're going to say water soluble. I'll show you some real data, or at least data I found on the internet in just a bit. So that is a 1 to 1, 2, 3, 4, 5. That's 25%. Sorry, 20%. An O to C ratio, or percentage. Should we say 20%? 1 to 1, 2, 3, 4, 5. And this one is a 1 to 2 ratio. Let me show you some real data. The first one is water solubility, and the names of these two molecules that we were comparing, ethanol and 1-pentanol, you could also call it ethyl alcohol and pentyl anywhere. Here, pentyl alcohol. So when it's miscible, it's saying that it's 100% soluble in water. But when you start getting these lower percentages, so I would say isobutyl alcohol is not soluble. It drops to only 10%. Okay. So 10%, I think, by volume. So 10 milliliters to 100 milliliters of water, that's the maximum limit. We had pentanol, or in this case, N-pentyl alcohol, down to 2.7. So really, I'm counting carbons and oxygens, and specifically carbons and OH groups. OH groups. Okay. Now they show us an interesting picture here. They're showing you how water surrounds, because let's remember that when we talk about dissolving, we're talking about solvation. Dissolving equals solvation. How does the water surround the molecule? Let me go over one other interesting example. Find it. Vitamins. Here's the structure for vitamin C. It's a pretty big molecule, but it has many oxygens. Vitamin C is water soluble. And why is it water soluble? Because it can hydrogen bond water very well. So mainly it's due to hydrogen bonding. Due to hydrogen bonding, and in some part, dipole-dipole interactions. For instance, this carbon-oxygen bond, this double bond right here, that oxygen's very partial negative, and this carbon's very partial positive. So that's vitamin C. Look at vitamin D. Look how many carbons there are compared to oxygens. Vitamin D is benzene soluble. It has, oh boy, does it give a molecular formula? Give me a molecular formula, please. I don't want to count carbons right now. It's definitely oxygen compared to carbon. It's definitely less than 25%. We have one oxygen. One oxygen to 1, 2, 3, 4, 5, 6. Let's estimate 20 carbons. So it's 1, I'll show you what I'm writing in just a bit, to about 20 carbons. That's definitely a nonpolar molecule. Okay. Why did it get so dark? Let me just brighten this up a little bit. Oh, okay. So vitamin C, we'll say it's polar, and vitamin D, we'll say it's nonpolar. Okay. Now, another way to say benzene soluble or not water soluble is fat soluble. Why is that the case? Vitamin D will collect in your fat deposits fat cells because fat is made up of hydrocarbon chains, long hydrocarbon chains. So fats are very nonpolar. For the last 5 minutes, let me go over a textbook problem. Maybe a couple textbook problems, just to show you what your professor may be expecting you to answer. Determine, for each solute, whether the solubility is greater in water or benzene. Water or benzene solubility. Okay, we have bromine, Br2, sodium iodide, carbon tetrachloride, and formaldehyde. We'll have to know the Lewis structure for that. I'm going kind of fast, so definitely test yourself. See if you could draw the Lewis structures for each of these. But let me show you the speed at which you should be able to analyze these on an exam. Br2 is diatomic. The Brs have a electronegativity difference of 0 because it's Br and Br. This is nonpolar. So therefore it's benzene soluble. Right? There's no dipole when you have diatomic molecules. No net molecular dipole. NaI, we got to know that this is ionic. And ionic salts are pretty soluble in water because you have ion dipole interactions. So this is water soluble. Again, you could always test yourself by pausing the video. Try these two. Ion dipole, intermolecular forces. CCl4 is symmetrical because it's tetrahedral. Using the wedges and dashes, we could draw something like this. And that is nonpolar. Because the dipoles cancel out, this is benzene soluble. And then formaldehyde is the C with an O and two H's, like that. I see a very strong bond dipole. Actually, another way you could show dipoles is to do partial charges. Partial negative, partial positive. So we have a net dipole, I think I used blue, going up. This is polar and water soluble. Okay. One major exception. So we said CCl4 is nonpolar. Okay? Because it's symmetrical. The bond dipoles cancel out. These four bond dipoles going towards chlorine cancel out based on geometry. But what about CH, Cl, CH3Cl? Well, this is interesting because we only have one chlorine, and we'll draw it in up position. The rest are hydrogens. And we only have one one bond dipole. So we do say this is polar, okay, because it has a net molecular dipole, but not water soluble. That's the surprising part to some people. So it's polar, but not water soluble. Chlorinated liquids are typically not soluble in water. This is just an exception that we just have to remember. Chlorinated liquids are not soluble in H2O. And actually, when you have a cell and you want to dissolve it to get its insides, like the DNA, you want to dissolve its nonpolar membrane. You know what people use in the biology lab? Use a chlorinated solvent. Use CH3Cl or dichloromethane to dissolve the nonpolar membrane, even though this is polar. Actually, both are polar, according to geometry. Okay. Um, there's one more example. Actually, let me just leave it at that. I want to give you one more term, and it's this idea with the ions. When you dissolve a salt in water, you form ions. Those ions make what's called a strong electrolyte solution. Because electrical charge can now go through the water because it's carried by these charges. So a strong electrolyte solution equals a solute that creates a lot of ions in solution. And I will stop there. But again, because of the exceptions that exist, you want to do a lot of practice problems to determine whether your molecule of interest is water soluble because they are polar, or if they are more benzene soluble or hexane soluble because they are nonpolar.